Welcome to Semantic Web Technologies. This is lecture number 5, Knowledge Representations Part 2. We are now focused on the Web Ontology language, and it's the third part of learning OWL. Okay, we start with a simple example. Here, for example, what I say is that two individuals are the same. Just let's take a look at this little knowledge base. So we define a wine, and we have an individual, Wegeler Rheingau Riesling, and this is a wine. And this wine is made of Riesling grapes, and we have the wine with the vintage year 2007. And we say that this wine is the same individual as one that is denoted with this crude identifier, like WRR 012345, for example. So these two are the same individuals. Then we say, of course, wine is a class, and wine is a subclass of alcoholic beverage, and alcoholic beverage is a class. What you can do now, for example, is in this knowledge base, you can also deduce, or you can make an inference that this individual, because it's the same that the individual here, must also be an alcoholic beverage. So this is quite simple. On the other hand, you also can state the difference of two individuals, and you have to do that because of the open world assumption. It's always possible, if you don't do that, that two individuals are probably the same. So you can denote OWL different from, and this says that two individuals are not the same. So for example, here I define another identifier as a wine. So this one, WRR 012346, is also a wine, and this is different from the other one we have already defined. So we have two different sorts of wine. And of course, sometimes you are looking at sets of individuals and you want to state that all of them are different from each other. Then you have also a shortcut here given in OWL, so you do not have to state the difference between each single pair of the set. What you have here, you can say, you can define a set, and you can say that all members of the set are all different from each other. You do this via the OWL all different class, and you define some node as belonging to the class OWL all different, and you say that the members of this class are an RDFS collection, and there you state all the individuals that are really different from each other. Okay, so that's difference and equivalence of individuals. If we remember, we have started with defining classes, defining properties. We have defined class hierarchies up to now. What's missing up to now is, for example, the so-called closed classes or nominals. So just remember, nominals and closed classes are classes that are defined by enumerating their members. Okay, we can do this also here in OWL. So let's take a look at the example we have here. We have defined wine again as a class, and then we have two French wine. The one is Chateau Latour Pauillac. It's a wine, and we have Chateau Lafite Rothschild. It's also a wine. And then we say, okay, we define another class. It's called red wines in store, and we say which wines we have in store. And in store, we only have wines of the following classes, or we have the following two wines, that's it, in this class or in the store. And these are the two wines we have defined here as an individual. And it also says that no other red wine is available in the store. In description logics, you can state this simple fact in the following ways. You say here, red wines in store, it's a class, and this is subclass of an enumerated class or a nominal, where you here enumerate all the individuals that belong to the class, and they are here in curly braces. Okay. Moreover, in OWL, as in description logics, we know we have so-called class constructors. And here, for example, we have the logical and, you know this, the conjunction, then the disjunction and the negation, and the corresponding OWL vocabulary is for the conjunction. It's OWL intersection of, so it corresponds to the set theoretic model of OWL. So it's like an intersection of two sets. Therefore, it's called intersection of. It's a property here. We will see how it is used right away. And then OWL union of denotes the logical disjunction, and OWL complement of denotes the logical negation. And as you know, these logical constructors are applied to create complex class descriptors from atomic classes. Okay, first example. Here we have an intersection, and what we say here is that the wines we have in store are defined as the things we have in store that are wines. So it's the intersection of things in store and wine. In OWL, you state this in the following way. You say wine is a class, things in store is a class. And then you define that wines in store is, again, a class, but this class is defined as the intersection of wine and things in store. So it's expressed pretty simple. Wines in store results from the intersection of all individuals of the classes things in store and wine. On the other hand, let's just take a look at the disjunction. Disjunction is OWL union of. So you see here we define wine. This is equivalent to the class of, or to the union of dry wines, medium wines, and sweet wines. So wines are consisting of dry wines, medium wines, and sweet wines. And we can state this in OWL in the following way. We say wine is an OWL class that is equivalent to, so we need here this OWL equivalent class expression. And then we state this in an empty node. You see this? And say here in this empty node, we define an empty node which consists of a union of the dry wines, the medium wines, and the sweet wines that, of course, before have to be defined as a class. But if we define it that way, we also know that this is a class. So you see here, we can define the class wine as the union of other classes. So that's no big deal. Okay, what else can we do? We have the complement, and of course, we can say that a class is completely different from another class. So for example, we say wine is no pizza. So these two classes are, of course, disjunctive. Then I can also state this in the way with description logic that I say here wine is the subclass of not pizza. And yeah, you can write it, of course, shorter with the disjoint with property. But you can also state this fact if you say wine is an OWL class and this is a subclass of the complement of pizza. So this is another way to define disjointness between two classes. Okay, so much for the class constructors. Let's take a look at properties and property restrictions. Property restrictions can come in two different sorts. On the one hand, we have, for example, the way to define existential and universal quantifiers on properties or roles. Or we can also say that a property must have a specific value, here with a has value property. And on the other hand, we can also make restrictions on the cardinality of properties, and this you can do with the OWL cardinality, or you can put upper and lower limits to a cardinality with OWL min cardinality and OWL max cardinality. You learn these things best when we take a look at examples. So first example, it's a property restriction with constants, and what we want to define here, you see it in description logics, we define Harald's causes, and Harald's causes is a subset of everything that is managed by Harald, by me. So quite simple, you say here, this is the individual, and you define an individual on that role or on that property by stating here or giving here the individual that restricts this role. So if you want to put this in OWL, it's also quite simple. You define Harald's causes as an OWL class, and then you say this is a subclass of a so-called OWL restriction. So the subclass here again is linked to an empty node, and this empty node is of the type OWL restriction. This means it is a property restriction which serves as a class constructor or a class definition. And we say here the restriction is on the property is managed by, and you do this with the OWL vocabulary on property. And then you state the value, which is given as a constant for this restriction, and you say OWL has value, and then you give here the constant that you have already defined previously. So it's the individual Harald. Okay, and what we have done here, we have defined a class, Harald's courses, and this is described via a fixed value assignment, it means a constant of the individual Harald to the property is managed by. So this is quite expressive, isn't it? Okay, but this is not the only way to restrict classes. So here again, you see what must be defined previously to make this definition. So we have person and course as a class, Harald as a person, and is managed by as an object property. Okay, let's take a look at the quantifiers. We start with the universal quantification, and you know universal quantification for description logics as well as for all works in the way that it fixes all instances of a specific class as allowed range for a property. So what we do here is we define wine, and we say all wines must have a winemaker as producer. Okay, and you define this in OWL in the following way. You say wine is a class, and this is a subclass of, and now again, we define a restriction on a property. So this empty node is of type OWL restriction, and this OWL restriction is on the property has producer, and of course, all values in the range of that producer are restricted to this class, and this is the class called winemaker. So therefore, we have here the producer, we have product, and we have winemaker, which are classes. And then we say a producer is an object property which has a product there and its producer on the other hand. So we have domain range descriptions here. And if you think this or take this as a prerequisite, then you can define here the following statement, which says that wine has always a winemaker as producer. So all values from, this is the universal quantification with OWL. Okay, now let's take a look at the existential quantification. We know from description logics that in existential quantification we define a class where we have a restriction on a property, and there must exist an individual for that property which belongs to a given class. So the class range is fixed here, or the property range is fixed. So for example, we can define someone who is a wine lover as somebody who likes wine, besides other things, of course. Therefore, we have here the existential quantification. So let's have a look at OWL. So we define a class wine lover as an OWL class, and we say this is the subclass of a restriction, and the restriction is on the property likes. And here we have the word from the OWL vocabulary, some values from, and this is the existential quantification or existential restriction on the property likes, and it says that there must exist an individual which belongs to the class wine, besides other individuals that each wine lover might also like. So here again, we have as a prerequisite that wine lover is a class, wine is a class, and likes is an object property, where we here don't restrict range and domain. Okay, so we have now universal quantification and existential quantification. In the end, let's have a look at the cardinality restrictions or number restrictions. Here, we can also have the possibility to restrict properties according the number on which they should apply. And we do this with the OWL vocabulary word OWL cardinality. This restricts to an exact number. Here, just as a reminder for OWL light, so the old version of OWL, OWL 1, and therefore the dialect OWL light, there was only allowed the restriction 0 and 1. For OWL DL and OWL 2, there the restriction in cardinality holds to any exact number. And on the other end, you can also set upper and lower bounds with the help of OWL min cardinality and OWL max cardinality. And now we can define a string quartet, and we say a string quartet always has exactly 4 members. And this, of course, can be defined in the following way. We say a string quartet is a class, and this class is a subclass of a restriction, and here we have OWL restriction on the property has members, and we say here that the exact number of members that we restrict here is 4. Again, here we have the prerequisite that has members as a data type property, which has as domain anything or a thing. So you see here the OWL top class, it's all thing, and we say that the range here must be an integer. So now we have almost all what we need for OWL, OWL property restrictions and stuff like that. Some special cases of the OWL vocabulary are still missing, and these cases we will consider in the next part of the lecture.